You know, on my way over here to record this video, I saw a string of ants walking across the sidewalk. And I kind of thought, I wonder what it's like growing up as an ant. I think it's really confusing to be a baby ant. I mean, I think it'd be hard if all of my uncles were ants too. Make things confusing. Anyway, today we want to talk about continuous random variables and continuous distributions. So previously we've talked about discrete random variables, a situation where the outcome of a random variable takes a finite number of outcomes, and we can create a probability distribution function by listing out all of those outcomes and the associated probabilities. We want to start talking about continuous random variables. These are random variables where the outcomes are generally measured and not counted, and have an infinite number of possible outcomes, and how we can deal with determining probabilities for events like those. So let's consider a situation where buses run on a pretty regular interval, and whenever you get to the bus stop, you're going to have to wait somewhere between 2 to 15 minutes. So we wait between 2 and 15 minutes. For a bus. And let's say that the likelihood of the bus arriving anywhere in that 2 to 15 minutes is equally likely. Now, what would be an answer for a question of what is the probability that we wait 10 minutes? For discrete random variables, we would just look up the outcome of wait 10 minutes on a chart, and that would give us our probability. But with continuous random variables, it's not so simple. So let's consider a graph, and let this be wait time, and let this be probability. And we're going to hand wave a little bit about what this probability part over here means for now. And so let's say that we've got 2 to 15 minutes over here, and that all of those are equally likely. So then imagine that we can represent the likelihood of these outcomes as a box of uniform height. And so with discrete random variables, we would say, okay, let's take all the outcomes between 2 and 15 and assign it a probability. And that's just the probability of that happening. But that quickly breaks down if we try to do that for a continuous random variable. Because between 2 and 15, all of the different times that we could wait, there's an infinite number of those. Saying I waited 10 minutes is saying I waited exactly 10.000000 minutes and not 10.001 minutes or 9.997 minutes. And so with an infinite number of outcomes, we have to ask ourselves, how do we assign probabilities for those? Because no matter how little probability you put on each one of those outcomes, there's an infinite number of them. And if we said that they're all equally likely, right, we have to have something non-zero that we can add up an infinite number of times and still get 1. And that doesn't happen. So with continuous random variables, we have this interesting situation where the probability of any one outcome is always 0. So we have our first rule, the probability that x is equal to some value c is always 0. And so if that's true, how do we ask questions of continuous random variables? Well, the answer is that we ask questions in terms of intervals. We ask questions like, what's the probability that you wait between 5 and 7 minutes? Or what's the probability that you wait more than 12 minutes? Or what's the probability that you don't have to wait any more than 4 minutes? These are the types of questions that we can ask for continuous random variables. And the way that that works is with a graph that looks like this. For a random variable, the graph like this of the likelihood of these outcomes is known as a probability density function. Now this is a little confusing because this has the same acronym PDF as probability distribution function that we used for discrete random variables. It helps that there's a PDF for both types of random variables, but the D stands for different things. And so with probability density functions, we don't assign probabilities to specific outcomes. Instead, we kind of slather the probability across all of the outcomes. So you can think about, we have a big jug of probability equal to 1, and we take that and we spread it over all of the outcomes. And the more we spread on certain areas, the more likely that we're to get outcomes in that area. And the less we spread it, the less likely we are to get outcomes in that area. But for this case, we have it spread evenly across 2 to 15 minutes. And so the probability of an interval occurring is just the area of the amount of probability contained in that interval. And so the first thing is we still have to operate under this idea that the probability of all of the area underneath this curve over all the outcomes is still 1. That still has to be true. And we still have to have everything above the x-axis. We still can't deal with negative probabilities. So those rules are still very similar, and that gives us that the probability that x is between C and D is just equal to the area of the area under the curve, or under the PDF, and above the x-axis between C and D. What's also interesting about continuous random variables and continuous density functions is that the probability of C less than or equal to x less than or equal to D is equal to the probability of C less than x less than D. Because remember, there is no probability at C. There's no probability at D. So including C and D or not including C and D is just removing the probability of those two endpoints. There's no probability at those two endpoints. So those two things are the same. So in this case, if we wanted to ask, what is the probability that we wait between 5 and 11 minutes? The way we would figure that out is we would calculate the area underneath here between 5 and 11, and that would give us our probability. So these probability density functions are going to be really important tools for us to study continuous random variables. And so most of what we're going to have to work with is determining what is the probability density function for different random variables.